I repeat. Good morning. We'll start with discrete communication channels, which is a part of digital communication system. We have seen a communication system which will have a transmitter and the receiver interconnected by channel, and this transmitter and receiver are split into different blocks in discrete communication system, wherein there is a discrete information source which generates a sequence of symbols, and parameters associated with this are entropy and entropy rate, which we have studied. These sequence of symbols are coded either in binary, ternary, quaternary, and so on. So the output of the source encoder is a stream of code symbols associated with the stream of source symbols. So this, if it is the source encoding is binary, then the output of source encoder is a stream of bits, which will have the message in the form of zeros and ones. Now these message stream of zeros and ones are added some extra bits called check bits by the channel coder, which will help in the receiver for the detection and correction of errors that happens when the information is communicated over a channel. So at the output of channel encoder, again it is a stream of bits if it is a binary communication, wherein this stream of bits will have message bits along with check bits, and each one of these stream of bits are converted into analog signal by modulation, discrete modulation schemes, and they are propagated or they are transmitted over a channel. Now this channel has got its own behavior for information transfer, and there is always a probability of error when the information is communicated over a channel because of its physical properties. So we need to analyze the behavior of the channel and the parameters associated with this channel for the purpose of analysis of information transfer over the channel, and the reverse process happens at the receiver. So this unit basically concentrates on the study of channels, wherein we'll be studying how the channel is, maybe wired or wireless channel, is represented mathematically, and entropy functions associated with the channel, then one more parameter called mutual information, then capacity of the channel, and some special channels is the content that we are covering under discrete communication channels as a part of unit 3. So this whole content might require some 2 to 3 sessions, wherein in today's session we'll be covering how is the mathematical representation of the channel and its entropy functions. So as a part of a discrete communication system, right, at point B, if you look at point B is the output of the source coder, wherein it is a stream of, at point B it is a stream of code symbols, source code symbols, and it can be binary, ternary, quaternary, and so on, wherein considering binary source coding, at point B it is a stream of message bits, and in turn some check bits are added in the channel encoder for error detection and correction purpose, and even at point C it is also a stream of code symbols, in particular binary symbols for digital communication, which are modulated here, and this whole thing is a channel, wherein this is the actual transmission medium, which is wired or wireless, and there is always a possibility of addition of noise, okay, in the channel, and this noise might lead to some error at the receiver. Okay, some of the bits might be erroneously received at the receiver because of the noise, which is there are a variety of parameters associated with the noise, due to which there is a possibility of receiving any of the bits erroneously. And to deal with the effect of noise for information transmission, right? What we'll be dealing with is this check bits which are added, which will help in detecting if there are any errors during transmission, and possibly it is possible to correct those errors at the channel decoder. Now again, after channel decoder, it is again the source decoding, and finally we arrive at a destination wherein the actual information, which is in the form of audio, video, text, image, anything that can be produced at the destination. Now what we see in this is there are three types of defining channels depending on from what point to what point in the discrete communication system we look at. So from point B, which is output of source encoder, to the output of the channel decoder, which is going into as an input to the source decoder, we represent it what is called as data communication channel, because at B it is the actual message, at the output also it is the actual message. Okay, because which we call it as a data communication channel. So at the output of a channel encoder to output of the demodulation, we call it as a coding channel. Okay, and these two both are discrete in nature in case of digital communication, wherein at the input and at the output of both these channels it is simply code symbols, which is binary in case of digital communication. Whereas the modulating channel is analog in nature, wherein once a stream of bits are modulated using discrete modulation system like ASK, PSK, FSK, the output of those modulation schemes are analog in nature, and which is this analog signal is communicated over the physical channel. Okay, wherein these two are transmitter, this is the receiver, and this physical wire, okay, or wireless channel along with addition of noise signal put together, we call it as a physical channel. So what we are studying as a part of discrete communication channels in this case is we are studying something called coding channel, wherein the stream of bits at the output of channel encoder, how they are physically represented in discrete communication system. So let's study mathematical modeling, how this physical channel can be represented mathematically. So if you look at any channel, whether it is a wired or wireless, to this channel we are feeding information which is discrete in nature. So we consider at the input of the channel, we consider sequence of code symbols x1, x2, x3, so on up to xm. Okay, so this set of code symbols at the input of the channel is represented with a variable x. Now totally there are m symbols, and this m is 2 if it is a binary communication. And because of the behavior of the channel, at the output it may not be exact, the number of symbols may not be exactly equal to m because of noise in the channel, right? So the output might be received which is different than these, if that all there are errors during transmission. So that is the reason the output symbols are y1, y2, so on up to n, wherein some of these might be the actual, and there can be some symbol which is not a part of the transmitted signal, and that is because of error in the channel. Okay, so at the output of the channel we represent n number of symbols, and these m and n, okay, might be equal, may not be equal, depending on the type of channel. So this channel, okay, which if we represent as a block, the input to this channel are so if you consider this as a physical channel which is wired or wireless, the number of inputs symbols are x1 to xm and number of output symbols are y1 to yn. So this is the channel. Okay. Now what we are studying is the mathematical representation of this channel, to which inputs are m symbols, outputs are n symbols. Okay. And in discrete, in binary communication system, m and n, if equal, okay, two symbols 0 and 1, output also 0 and 1. Now this behavior of this channel, the mathematical representation of this channel, how it is being modeled is the discrete communication channel is completely modeled by the set of probabilities. Okay. So this probability is probability of the input symbol transmitted and transition probability Piz. Okay. What is the probability that, okay, what is the probability of the symbol received is Z, knowing that we have transmitted Xi. Okay. So this Piz, again we will be looking at, is what we call transition probability. So this discrete communication channel is represented by a set of probabilities called input symbol transmission probabilities and Piz called transition probabilities. So this transition probability is a conditional probability. Okay. Transitional probability is like conditional probability P of Yj given Xi. Okay, knowing that we have transmitted a symbol, we know that we have transmitted a symbol Xi. What is its probability that the received symbol is Yj, called transition probability Piz. Now we will be looking at the mathematical modeling of this physical channel with the probabilities Pit, probability of the transmitted symbol being Pi. Transition probability is a conditional probability. So for binary channel, diagrammatically we can represent this physical channel in the form of diagram like this, wherein the input symbols are 0 and 1, okay, in binary, and output symbol received will also be 0 and 1. Now this channel, okay, binary channel, is represented by two symbol probabilities. Probability that the transmitted symbol will be 0, we call it as P0t. Probability that x is 0 is P0t. Probability that transmitted symbol is 1. Okay, probability that x equal to 1, P1t. Similarly, at the output also, probability that the received symbol is 0, P0r. Probability that received symbol is 1, P1r. So these are the probabilities of the symbols at the input side and at the output side. And there is something called transition probability. Okay, transition probability Piz. What is the probability of receiving the output symbol, the probability that the received symbol is J, knowing that we have transmitted the symbol I, which we call it as Piz, called transition. So P00 means that what is the probability that the received symbol is 0, knowing that we have transmitted 0. Okay. If you look at this transmitted 0, if correctly received, it is P00. Transmitted symbol is 0, received symbol is also 0. So because of the noise in the channel, the transmitted symbol might be 0, but it can be received as erroneous symbol 1, whose transition probability is P01, meaning that we have transmitted 0 but received it as 1, Piz. Okay. So what is that probability that received symbol is 1, knowing that we have transmitted 0? We call it as P01. Similarly for P10, which is erroneous transmission, and P11, which is correct transmission. And sum of all these probabilities, okay, when we transmit any symbol, it's a sure event that it is going to be received at the receiver end. Whether correctly or incorrectly, that is the second part. But once a symbol is transmitted, it is been or it will be received, which is a sure event. Hence, once we add these transition probabilities, it should be equal to 1. Now what is the probability of error? We are estimating what is the probability of error for any channel. Okay? So most important component in studying or in analyzing any channel is what is the probability of error. That is one of the important parameters. So one can be erroneous reception or erroneous transmission is transmitted symbol is 0, received symbol is 1, which is error. Transmitted symbol is 1, and if it is received as 0, that is error. So probability of error is probability of Y received is not same as what was transmitted. Okay? If it is different. So probability that transmitted symbol is 0 and received as 1, or probability that transmitted symbol is 1 and received as 0. So X is transmitted symbol, Y is received symbol. So if it is other 0 transmitted, 1 received, 1 transmitted, 0 received is what we call it as error, and this is something called a joint. Okay, this X0 Y1 is a joint. Okay, this X1 Y0 is a joint. So this joint probability can be expressed as conditional probability using probability theory. So we have studied in probability theory probability of event A knowing that event B has occurred is the joint probability divided by probability of conditioning event. So this event we call it as conditioning event, and this is what we call conditioned. Okay. So this event is conditioning this. We can say that event B is conditioning event A. Putting in the other way, event A is conditioned by event B. Okay. So A is conditioned by event B, or B is conditioning event A. Probability, we know B, so what is the probability of A, occurrence of A? That is what we call conditional probability, which is related as joint probability divided by probability of the conditioning event. Now what we see here is a joint. Okay, it is a joint probability of X and Y. X0 Y1 joint, X1 Y0 is a joint. Okay, to call it as a probability error. This can be expressed in terms of conditional probabilities and input probabilities. So this joint probability, if you look at probability of this conditional probability divided into probability of conditioning event. So using this relation, we express the probability of error. Just joint probability translated into conditional probability and probability of conditioning event. The same in short form, P0 transmitted and transition probability is P01. P1 transmitted, probability of transmitted symbol is 1 and transition probability is 10. Okay, we call it as a probability of error. On the same line, okay, we can also express P0R and P1R, received symbol 0, received symbol 1. So if you analyze at the output side, okay, so these equations are at the input side. So if I analyze the probability of symbols at the output side, okay, what is the probability that we receive a 0? We can receive a 0 when transmitted symbol is 0 with a conditional probability, with a transition probability P00, or we can receive 0 when the transmitted symbol is 1 with the transition probability 10. So we can receive 0 when 0 is transmitted and transition probability is 00, or we can receive 1, okay, when the transmitted symbol is 1 and with a transition probability 10. Similarly, when can we receive 1 is, we can receive 1 when 0 is transmitted with a transition probability P01, or we can receive 1 when 1 is transmitted with a transition probability P11. So we can also express received symbol if we are at the output side. So same concept which we have analyzed, these mathematical diagrammatic representation of behavior of the channel and their corresponding mathematical expressions or mathematical form of operation of this physical channel, which is binary in nature, can be extended to ternary, quaternary, in general, these m number of symbols. Okay, in general, m number of symbols, received symbols are n. How can we represent? Like how we have written the diagrammatic representation of a binary channel, similarly we can in generally represent the operation of a channel diagrammatically, wherein the inputs are m, x1, x2, x3, so on up to xi and finally xm. Received symbol are y1, y2, so on up to yn. So in general, we are looking at some ith symbol and jth symbol. So this symbol 1, okay, is received as symbol 1, okay, with a transition probability p11 and transmitted probabilities p of x equal to 1, okay, x equal to 2. So likewise, a particular symbol might be received as y1, y2, so on up to yn. So it is connected to all the n nodes. Okay. So if you look in general, if you look at any ith symbol, it may be received as 1, may be received as 2, may be received as j, may be received as n. Okay. So at the input side, if you know that we are transmitting xi, it can be received as one among the y symbols. On the other side, if we are at the receiver side, we have received some single symbol yj. What is the symbol being transmitted? Okay, so that also we can estimate. Okay, that also we can estimate if we are at the output side. So if we have received yj, the transmitted symbol can be 1 or 2 or I or any one of these m symbols. So analysis can be done being at the input side or being at the output side, knowing the symbol transmitted symbol probabilities and the transition probabilities, or knowing the output symbol probabilities and the transition probabilities. And accordingly, on the same line, we can estimate probability of error. So transmitted symbol I is represented, probability of transmitted symbol is I, probability of received symbol is j. And this is a conditional probability. Probability of error is whenever transmitted symbol and received symbol are not same. That is the probability of error. So in this case, what is the probability of error is when we transmit a particular symbol, okay, what is the probability that it is received as? On the similar line, how we have analyzed the probability of error here, okay, on the same line, we estimate the probability of error, okay, for in the general case for m number of input symbols and n number of output symbols. So what is most important to understand here is any physical channel, may be wired or wireless, is represented mathematically, diagrammatically, okay, by a diagram called channel diagram, which will have input symbol probabilities, transition probabilities, and accordingly we can estimate output symbol probabilities. So mathematical representation of a channel, any physical channel, in the form of a diagram called channel diagram and their corresponding parameters, and accordingly, most importantly, we can estimate what is the probability of error for a given type of channel, maybe wired or wireless. So let's look at some more mathematical representation of this channel. What we saw was diagrammatic representation, and the same can be represented in the form of what we call matrix. Okay, so diagrammatic representation is one form of representation. We can also represent the behavior of the channel in the form of a matrix. So these input symbols we are considering x1 to xm with probabilities p of x1 so on up to p of x1, such that sum of all these probabilities will be always equal to 1. Similarly, output symbols are n, and sum of all these output symbol probabilities should also be 1. So a very convenient way of representing these discrete channels will be in the form of matrix called channel matrix. So that is a diagrammatic representation of the channel. This is a matrix form of representation of the channel. Hence, this P y given S conditional probability matrix, we call it as a channel matrix. matrix form of representation of operation of the channel. Okay, wherein if you look at this, all these rows are representing input symbols, columns are representing output symbols. So we have m symbols at the input. Okay, so there are m rows. There are n symbols at the output, so there are n columns. So it is a m by n matrix. Okay, m rows and n columns, input and output. So for a particular symbol x1, we can receive it as y1 or y2 or so on up to yn for the symbol transmitted x1. y1 given x1, y2 given x1, yn given x1. So if we know that we have transmitted x1, okay, what is the probability that it is received as y1 or y2 or yn? That is what we call it as first row of the channel matrix for the transmitted symbol x1. Similarly for x2, y1, it is received as y1, transmitted symbol is x2. So this x2 can be received as y1 or y2 so on up to yn. Likewise, mth symbol y1, y2 so on up to yn. Similarly, okay, this is if you analyze this matrix on the row side, we know these transmitted symbol probabilities, and accordingly we can estimate, okay, what can be the received symbol. Is it correctly received or erroneously received? On the other side, if you look at column wise, okay, if you look at column wise, we have received y1. We have received y1. What is the probability that the transmitted symbol is x1 or x2 or so on up to xn? Okay, column wise, we can analyze the channel being at the output side. So the diagrammatic form of the channel, can also be represented in the form of a matrix. Okay, so that is a channel diagram, and this is called a channel matrix. So two representations of any physical channel: diagrammatic representation of the channel called a channel diagram, matrix representation of the channel called channel matrix. Y given x is a channel matrix. Okay, this matrix is called channel matrix. Now this channel matrix is a conditional matrix. Now this conditional matrix can be expressed in terms of joint event matrix, joint event probability divided by probability of the conditioning event. So this channel matrix can be expressed using this relation. Okay. So this is a channel matrix, okay, which can be expressed. This is a channel matrix. Okay. So one is diagrammatic representation, second is the channel matrix, and third representation of channel is what we call JPM, joint probability matrix. Is a third representation of a channel. So this joint probability is joint event. Okay, a particular symbol transmitted, a particular symbol received. So it is pair. It is a pair. Transmitted symbol and received symbol is a pair, which is called as a joint probability. So this joint probability can be expressed as this channel matrix probability P x given y divided by multiplied by P of y. This relation. Okay. So x1 given y1 probability of the transmitted symbol. This is another representation of the channel, which we call it as a JPM, and this relation we call it as a joint probability P of xy, x1 y1, x2 y2, x1 y2, x1. So row is transmitted symbol and column is received symbol. So what we saw as a part of mathematical representation is we can represent the behavior of any physical channel in three different forms. One is diagrammatic representation called the channel diagram. Second is matrix representation, which we call it as channel matrix. Third representation is again a matrix representation called joint probability matrix. Okay, this is so three different representations, mathematical representation of the channel: diagram, channel matrix, and joint probability matrix. This is joint probability representation. Now let's look at what are the fundamental properties of joint probability matrix. If the channel is mathematically represented in the form of JPM, joint probability matrix, the element of the matrix, if you look at the matrix as a whole, it has got certain structure. Okay, it has got certain structure, and that we define in the form of what is called properties of JPM. So we have JPM. Okay, we have JPM, and this JPM, if you add the elements column wise, if you add the elements of the JPM column wise, okay. So if you add the elements of the JPM column wise, so what is common in column wise is output symbol. So if we add the elements of the JPM column wise, what we get is probability of receiving Y1. If we add second column, we get the probability of receiving Y2. So column wise addition will give us probability of received symbols. Row wise addition. So what is common in row wise is x1, x1, x1. So if we add the elements of JPM row wise, we get the probability of input symbol. So one fundamental property is adding column wise, we get the probability of output symbol. Second property is adding row wise, we'll get the probability of input symbols. And third property is if you add all the elements of JPM, if we add all the elements of the JPM, that will always be equal to 1. Okay. So sum of elements of JPM, all the elements of JPM is equal to 1 is the third property. So mathematical representation is if you add column wise with I varying, okay, row is varying here. In column wise addition, column remains a constant, row is varying, I is varying. So if you add column wise, we get the probability of output. Here J is varying, okay, column is varying, whereas a row is fixed. What we get is the input symbol. And if you add all the elements, okay, with I and J all varying, okay, the sum will be equal to 1. Now, another important point with regard to elements, what these elements of JPM basically indicate. Now, this matrix, okay, will have transmitted symbol, received symbol. Okay, likewise, elements will be there, so on. Okay, so many elements will be there, and these elements, okay, these diagonal elements, what they indicate, what they represent actually, if you look at the matrix, diagonal elements, okay, transmitted symbol is x1, received symbol is y1, transmitted symbol is x2, received is y2, transmitted symbol x3, y3, xm, if m and n are equal, xm, ym. So if you look at this, okay, what they represent is the symbol transmitted is received, the corresponding symbol. Okay. And suppose all other elements are 0 except the principal diagonal elements of this JPM. What this matrix representation of a channel indicates. So if all the elements other than principal diagonal elements are 0, both on the bottom side and the upper side of the diagonal element, this is ideal channel. Okay, ideal channel, which means that under no case the transmitted symbol is 1 and received is something else. So there is absolutely no error in the transmission, and that channel we call it as a ideal channel, and another term is what we call noiseless channel. and that is what the statement indicates here. Okay. The probabilities along the principal diagonal element of a JPM gives the noise condition. If all these principal diagonal probabilities are 1, then probabilities outside the principal diagonal are 0. Then the channel is called ideal channel or noiseless channel. So this JPM describes the noise characteristics of the channel. JPM always describes how is the noise behavior of the channel. So what we expect for a better channel is all these other elements other than principal diagonal elements must be 0 for a better channel. Okay, if all the other elements are 0, then that is the best. And while designing any physical channel or while studying any channel, what we try to do is we try to make these elements other than principal diagonal elements, we try to make them 0 so that we can have better transmission. Okay. So if it is a physical channel, no doubt we can take certain measures in the design of that physical channel. If it is a wireless channel, then some things are not in the control of any human being. These are natural, and because of which we incorporate something called error detection and error correction method. So as a mathematical representation, right? So principal diagonal elements other than principal diagonal elements, if all are 0, then that is ideal channel or noiseless channel. Hence we say that this joint probability matrix describes the noise characteristics of the channel. So 3 mathematical representations: channel diagram, channel matrix, and JPM. And 3 important properties of JPM: adding row wise we get input symbol probability, adding column wise we get output symbol probabilities, and adding all the elements will always be equal to 1. And if other than principal diagonal elements are all 0 in JPM, okay, that is the ideal or noiseless channel. Hence JPM describes the noise characteristics of any channel. Now next look at entropy functions. Okay, it's the second bit of our study. First bit is mathematical representation in 3 different forms. Then entropy functions associated with any discrete channel. We all know what entropy is. We have studied in the first unit what entropy is. Average information per symbol. Okay, so if it is binary, what is the average information 0 is conveying? How much is the information 1 is conveying on an average? So if there are m number of symbols, on an average, how much information each symbol is going to convey. Now with respect to transmission, with respect to channel is a medium of information transmission between transmitter and receiver. So with respect to this entropy in channels, okay, on an average, how much information a particular symbol is transmitting. Okay, so there it is conveying. If it is a source, we are saying how much information it is conveying. When it comes to channel, okay, we say it is how much on an average each symbol is transmitting, or how many bits of information. So how much information conveyed through a particular symbol when transmitted over a particular channel is what we call entropy function associated with discrete channels. And there are various entropy functions: entropy at the input, entropy at the output, joint entropy, conditional entropy. Okay, different entropy functions are there and corresponding mathematical expressions. Entropy at the input, which we call it as entropy of the source, average information per symbol transmitted by the source, okay, is what we call h of x, entropy of all the input symbols, m input symbols, okay, transmitted symbols. Entropy of the receiver, okay, h of y, on an average, if you receive a particular symbol, how much information we received from the channel on an average. That is entropy of the receiver, h of y, okay, which is all n symbols received, pi log 1 by pi bits per symbol if the base is 2. Joint entropy. Third entropy function is joint. Okay, how there is a joint probability, there is a joint entropy. Okay, this is obtained from JPM. H of xy is for all I varying from 1 to m, j varying from 1. P of xi log 1 divided by p of xi. Joint entropy, which is obtained from joint matrix. Then conditional entropy. Okay, we can have two conditional entropies, x given y given x. Okay, both are the input as well as output. So x given y, probability of x given y. Now given y in the sense, we know that we have received a particular symbol, we are at the output side. What is the probability of transmitted symbol? P of y given x. We know that we have transmitted a particular symbol x. What is the probability that it is received as yj? We know that we have transmitted xi here. And associated with this, if you calculate the entropy, okay, that is one conditional entropy. Associated with this, if you calculate entropy, that is the other conditional entropy. So this is, one is called input conditional entropy, other is called output conditional entropy. So accordingly, conditional entropies, they are also called equivocation. Another term used for conditional entropy is equivocation, h of x given y given x. So these are obtained from JPM and conditional matrix. Okay, so h of x given y is p of xy log 1 divided by p of x given yj. If it is y given x, then joint probability is the same. Here it is y given x. So what is the change in this x given y given x is this. So this remains common in both conditional probabilities. So what this h of x given y indicates is, it specifies the average amount of information needed to specify a input symbol, provided we are allowed to make an observation on the output produced. We know the output, so what is the probability that received transmitted symbol is x. Similarly for y given x. Okay. So x given y is output conditional probability entropy. Y given x is a input conditional entropy. So these are the four entropy functions: entropy of the source, entropy of the receiver, and joint entropy, and two conditional entropies. Okay. So these are the four entropy functions associated with any discrete communication channel. So in the next class, what we say is, we say the relation between these four entropy functions. So entropy functions are entropy of the source, entropy of the receiver, joint entropy, and so these are the four entropy functions associated with any discrete channel. So in the next session, what we'll see is, there are certain relations between these entropy functions. Okay, and their corresponding proof we will take up in the next class.